And Carlos Rios is our digital media expert who could not be here either because he was up late last night uploading a gigabyte video onto some server. And we are from the Georgia Institute of Technology, the School of Aerospace Engineering. So here's a, I forgot, yeah. Here's a summary of the paper. Yes, there is a huge need for electric power worldwide, and our perspective in the US and Western nations, or even Japan, may be a bit distorted because we tend to think in terms of competing with the extremely efficient grids that we have and our extremely efficient utilities. And that is not the reality in most of the world. In most of the world, the power cost that people might afford to pay may be low, but only because it is heavily subsidized by the government, which is really not a sustainable situation to expand. So we should not just limit our thinking to competing with the $10 per kilowatt hour, et cetera, et cetera. And the people who don't have any money actually pay exorbitant costs for the first few watts or watt hours that they use. Even if I take the argument, I don't have to take the argument that having the power to make a 911 call is a life and death situation which cannot be measured in money. I don't really have to make that argument because the reality is that if you look at the cost that people actually pay for the alternatives to having a nice power grid, they are truly exorbitant. So again, we should think a little bit beyond these things. What space solar power in general does allow, and the concept that we are presenting does allow, is delivering power even on a retail basis to people who don't have any other means of getting to that. Now, we have this crazy scheme that I call the space power grid. And the basic difference in the thinking there is, I say, let us not try to fight with the terrestrial energy community. We are not big enough. We cannot beat them up. They will beat us up. Or they will just ignore us, which is what has been happening. However, they have serious problems, as you just saw. And the renewable power community has very serious problems. They cannot compete with the nuclear or cannot even compete with other things. Europe is facing extreme problems with the move to go to wind energy and all these things. So they have serious problems, and maybe we can help them. So that's what we say. Forget about generating power in space for a few years. It's not going to happen anyway, not in a few years. Use those years to actually help the terrestrial renewable energy community find its legs. Everybody will love us for that. And then bring in space solar power, at which point we're not hurting anybody because there's plenty to go around. So that's, and we think that can work with the usual, as John Mankin says, anything can be shown by computer graphics. Okay. And suitably adjusted economic modeling. But I think with reasonable parameters, we can show that this can be made economically viable. So in this, what has happened very recently is that there is strong interest in US-India collaboration that involves the space program. And that provides, and energy, and space, and solar power. And this has been identified as a very strong reason for collaboration in space solar power. So that is what we see as an opportunity there. Just a very brief overview. That's what I'm going to go through, and I'm just, okay, go on. We all love space solar power. I don't have to argue that here. That's a picture from the cover of New Scientist magazine. Actually, my students found really where it came from. And the basic point argued is that 1 square meter in space of collector, converter, whatever, is equivalent to 43 square meters on the ground. Okay, I leave that there. And I did present these things somewhere, and somebody from Europe said, but you have to show that this is better than fusion. And fortunately, it didn't occur to me to say, and your point is, because it is fusion power, except that we don't have to deal with all the problems of fusion power. It's given to us free, just have to bring it down. I didn't think that would go over well. Okay, go on. Now I go on to my slides. Space solar power, so I think my students put in something to NASA, which was reviewed, and the only thing they liked about it was that they said, oh, this deals with the idea of space solar power, which is a really neat new concept that NASA is interested in. I'm sorry, it is not new. It is really old. And cynical people like me can sit there and identify with our, wherever we sit, and look at the pies in the sky and say, there is a correlation between the periodic spikes up and down in interest in space solar power and national policy priorities of that period. Okay? So I think if you look at Peter Glaser, you know, I found out, who was Peter Glaser? Do you know? He was vice president of Arthur D. Little Company, whose expertise is not in space, but in strategic consulting and all these things. Made a neat argument for why you needed huge number of launches of renewable space vehicles, arguing that the cost would come down hugely if the number of launches was very high. And the case was made to Congress that the space shuttle would only cost $100 a pound to low Earth orbit. All right? Because the market was there, tens of thousands of launches. Okay, I don't want to go through all those things. So most recently, there is strong interest generated by the global warming concerns that were raised mostly by the Europeans a few years ago. And India and China were under pressure to do something about it. They were not officially obliged to do anything under the Kyoto Protocol, but that was one of the sticking points. So in the new version, people would like to bring India and China on board with carbon reduction initiatives. And one of the great ways to do that was to go to solar power. And then it was, that looks like a really neat way to, and there's other reasons. The et cetera is other reasons for space collaboration, which I'm not going to get into because I do not want to be stopped at the airport when I go to India. So we will just leave it there and point out that there is a strong reason for an India-US strategic partnership that involves space and solar power. Okay, next one. That is my next point. So why hasn't it happened? It's because it's hard. Okay, this Ngorongoro crater in Tanzania, I found while I've only been through the internet in the course of finding out something else. It is a very large game sanctuary that is located at a high altitude. It's a volcanic crater. And I have to point out that it's very large, but its diameter is smaller than most of the ground receivers that have been proposed under geosynchronous orbit-based space solar power. The animals there have, of course, there are some very heavyweight things. I'm not showing the small ones like me that are also running around there. They can't go anywhere, okay, because it's surrounded by steep hills and pretty, whatever it is. It's not easy to get out. Now, one could think of many ways that one could get out of there, but there are always some routes evident that look easy, but you don't know what you don't know. What is beyond? Are you going to run into something very hugely difficult beyond that is going to stop you? You just don't know that. So different people proposed this, and I'm not going to shoot down anybody because I don't know. And so some people argue that launch costs will come down. Some people argue that photovoltaic efficiency can be increased greatly. Some argue that the power per unit mass that is needed in orbit can be brought up hugely. I happen to believe some of that. Of course, my suggestion is to go to millimeter wave beaming, which is not possible today. But I think that is the right approach to take. And just coincidentally, you see that that is really the lowest point and that sharp canyon up there. Okay. So go on. Here's why. The chart on the right above is log to base 10 of receiver diameter in meters. The horizontal axis is beaming distance in thousands of kilometers. So if you look at a 2,000 kilometer orbit and you use 220 gigahertz, then you are at about 1 point something on the log scale. If you use 2.45 gigahertz, you are at 3 point something. And you go to geosynchronous, you are nearly 5. That's several orders of magnitude away. Okay? If you could go to lasers, which is the green dots, you're really in good shape. So I think there is a strong case to go to lasers, but I don't think that's there yet either. So these are the issues. You can't go to millimeter wave immediately, because even if you did and you had the conversion efficiency, you can't do this from GEO, because anyway the receiver is going to be large. You can't say that, oh, when it rains, by the way, you're not going to get anything. So you have to deal with the rain problem. I do believe, but of course this is one of those unknowable obstacle routes. I do believe that the rain problem can actually be dealt with. And they can create high efficiency paths. If you are dealing not with low level signal that you're trying to see from the stars, but you're dealing with 60 megawatt beams that you're going to beam for several minutes. You might lose the first minute, but anyway, we don't want to get into that. But this is the route that I see. So I'm saying I don't think any government is going to invest several trillions of dollars in space solar power before first revenue. I know how much money the Indian government has, at least outside whatever you hear in the newspapers about Swiss bank accounts. But they don't have that. Neither does the US government, actually. And 1 trillion is not going to get to first power by GEO-based space solar power and will not lead to scale up to the terawatt levels that are needed. Let's go on. So I have developed what I call the Ngorongoro crater viability parameter from many hours spent on Fortran programs trying to make things work. Saying, what does it really take to make this thing viable at a reasonable cost? And so that's where that number 25,000 comes from. It's not magically 25,000. It's somewhere approximate. The P is the price that you can charge for space-generated power. And I'm not using 10 cents a kilowatt hour. Let's say 20 cents a kilowatt hour. Efficiency is the efficiency of conversion from the first electric power that you generate, be it DC or AC, to the beamed whatever and received on the ground. Say you can get up to 50% eventually there. The S is the specific power, the power generated per unit mass in space. So that's a technology parameter. You have to increase that as much as you can. And the C is the launch cost dollars per kilogram to low Earth orbit, where I define low Earth orbit as the place where you can do the rest using really high specific impulse, whatever. And here's where we are. I think we are not that far away in the price. The efficiency, we are far away somewhat, but I don't really know how much. The cost to low Earth orbit, we may be not that far away. And the specific power, yes, we are way down. Okay, and that's usually the problem that is identified. And the other thing that I have not shown is the ground receiver diameter. I do not believe that, at least in India, you're going to find 100-kilometer diameter anything as a receiver. I know personally the people who will go out there and sit there with the flags protesting that. Let's go on. So here's our approach. We say in phase one, revenue comes by beaming terrestrial power to terrestrial and space-based customers. This was originally conceived as a solution in some class at Georgia Tech, where a student came and asked me, though they want to know what we would do to counter global warming. And I said, we are aerospace engineers. Why don't we beam the power out? And then we said, who would be stupid enough to do that? So that's what led to that thinking. Anyway, so we say eventually we might build up. So what we are doing is, there's no magic here. We exchange the launch cost risk for substantial technology risk of millimeter wave. And say, look, we are talking about something that's going to happen 15, 20 years away. Maybe there's a solution in millimeter wave. I don't know. I don't know enough electrical engineering to solve it. But I think I've looked enough to see that there are possible solutions. So that this system will break even inside 17 years, and you need to replace these satellites in about that time, according to the GPS constellation and things like that. So at that point, you start power beaming. You actually start power generation, and there's no escape. You're putting in huge, massive things. But at that point, you don't have to deal with all these policy arguments and this and that, and and you don't have to answer anybody on whether there is a market. You know there is a market. So that's it. Then you scale up. And how you scale up, it depends on national policy. You don't have to have continuous beaming all the time. We looked into this, and we realized that if you have satellites coming by one after the other between about 1 o'clock and 4 o'clock in the afternoon in a sunny place, and delivering power in the depths of the night somewhere else, people are probably going to be happy with that. So you don't have to wait until you have 100 to have this system. You can start off with a very small number, which leads to our argument. So as far as these satellites, what are we talking about? The initial sets of satellites are just relays. They do not convert at all. And that's, again, easy to do in computer graphics and a little bit harder to do the detailed design. I know that. But as one of my high schoolers said when asked, how are you going to build all these interplanetary postal system or something, she said, that's why we have a $4 billion development budget. We'll hire smart engineers. Okay. When we get to the conversion satellites, there's no magic again. We are talking about really huge 856 metric tons. The reflectors in high orbits are not that massive. The difference in cost between these orbits is not that high because you're going to be using continuous thrust, spiral orbit type of things. But so anyway, that's what we're looking at. Okay, let's go on. I have done the economics to the extent that I know. But if I were that good at it, would I be standing here instead of sitting out on the beach somewhere enjoying my billions? Okay. So we have shown that the system will kind of break even, reach zero net present value with a reasonable return on investment, not a venture capital type, but consortium, government-private consortium type agreement. You can do it. And then the rest takes a huge investment, and that is a matter of national policy. If you start investing very fast and launch these gigawatt type things faster, you'll go down deep into debt, but they are generating power. If you don't do that, you can make money quicker, but then it'll take much longer to replace the fossil fuels. Okay, let's go on. We have done some sanity checks. I do worry about these things, from time to time. And so we checked with the reports generated by the Aerospace Corporation around 2001 or so, comparing several architectures and doing a sane cost assessment. And here's the difference. So yes, there's a factor of 10 difference in mass in orbit between us and them. And where does this come from? We are assuming a higher specific power, yes, but there's a huge difference because we don't have these massive 5.8 gigahertz antenna and things like that in geosynchronous orbit. Okay, so it is reasonable, and yet we do, but there you're assuming $400 a pound to orbit, so I can complain about that. But anyway, so it's kind of in the ballpark. It's reasonable. Let's go on. Now we get to the US-India thing. So yes, I have in the paper discussion on why this is important and the realities in India and all these kind of things, which I don't want to go into. But what we have done is to see what does it take to start this up. And so we said, we've tried, we meaning they, my co-authors have tried systems with three satellites, 4 satellites, up to 6 satellites. And we had to go to 5,500 kilometers, not 2,000 kilometers initially, because this number was so low, and we wanted to trade clear across to the other side of the world. So you had to have that many satellites. And we looked at scenarios where there were 4 ground facilities. The one in India was taken to be near Mumbai, which is what everybody's heard about. I don't think that's the right place for it. US, New Mexico is the right place for it because it's a high dry plateau. Middle East, near Cairo, we figured if we said Egypt, the guys in the dark glasses would not come looking for us. Okay. So there was some, I said, look, yes, make an objective engineering choice, but don't get me into really serious trouble. Anyway, Western Australia, or we said 2 facilities, only India and US. Okay, how would we do this? So they have done this, and Nicholas would really like to spend the next half hour showing his videos, but I think they have that in the exhibit hall, and they will be talking about it on Saturday, I believe. Okay, go on. So one scenario was with 6 satellites, 4 ground stations, and I might actually ask them to comment on this if I'm wrong, but the question was, can you achieve essentially 24-hour continuous beaming with these, right? So you could do this with 6 satellites, or you could do it with 4 satellites, 4 ground stations, and okay, go on. And if we said no, only US and India, then you could do it with 6 satellites, of which only 4 are being used at any time. But Nicholas now tells me that, no, I didn't have enough faith in him, that you can actually do this with 4 satellites only, right? So yes, that can be done. 5,500 kilometers is still going to be larger collectors and all these things, but this for the demonstration purposes. Once you have these things going, you would expand the number of satellites, and then you could bring the orbit down quite a lot. Okay. So here you go. Yes, it needs a lot of technology demonstrations. And I would say you have to demonstrate dynamic power beaming. So it's not like I don't know all the showstoppers. I don't think that any of them are showstoppers. These are things where I think R&D can get there or is already there in parts of the government that will not talk about it. But from reading the papers, it looks like it's not that far. There is a lot of work and investment going into automobile radar, though that's at frequencies that are guaranteed to get absorbed in a short time. but 220 gigahertz is actually one that is very efficient for, it is a good window, and I have confirmation on that from people working in there. So we have gone through, if we go through these things, which will not happen in a year or maybe not even 10 years, I think then we can lead naturally to this system. Okay. So these are conclusions. Well, yes, renewed interest must be viewed with healthy skepticism, but careful analysis of the opportunities. The scale is simply large. It poses immense difficulties. So I think in 1979, NASA and DOE concluded that there are no real technical difficulties with space solar power. It just takes a lot of money, and by 2050, the US government will probably do that. There are major technical difficulties because the architecture does not work unless you are willing to make some big changes, which did not exist at that time, but I think can be done either now or in the near future. So those are really my conclusions there. I have one more thing there, which I had to tell you because I've published it somewhere else. I think we had to start thinking in terms of primary gas turbine power generation. If you have highly intensified power instead of highly intensified photovoltaic only, because highly intensified photovoltaic still leaves you with a huge active cooling problem. And the more you look at that, you start thinking, why are we doing this? Why don't we use active, instead of active cooling, why don't we use a gas turbine? Because they achieve immense values of specific power. Okay, last slide. Well, I think acknowledgement, yes, actually NASA in some form pays me to come to these conferences, and that's why. And my very last slide. So the AIAA has this thing that says, when did you know that you wanted to be an aerospace engineer? Yeah, nobody has asked me yet, but so I'm volunteering my answer. I saw this movie, I had not read the book, but I read the movie in the 1960s, before the moon landing, mind you. And the story is that the US and Soviet Union were trying very hard to show that they were in the space program for the, we came in peace for all mankind or humankind, etc., whatever it is. So they gave money to this country. And you can see what the government really needed the money for. But they had to show, the sponsors' visits would be there, so they had to show that they had a space program. And they put this mad professor in charge of that. And well, they actually came up with a solution. And at that point, the US and Soviet Union got really interested, and they nearly beat them to the moon. So the thing that really, the dramatic, scientific, quasi-scientific part of that was the part where these people from Fenwick were standing on the moon, and the US and the Soviet landing capsules come zooming down, racing to the last minute because they can't slow down because the other will win, and go right into the surface, because at that time, if you remember, many people believed that the lunar surface was dust down to 30 meters. So they just went into the dust, and then of course, they were pulled out. So thank you very much. That's my take on this. So and yeah, that's from old, at a very low altitude beaming. Thank you very much. For a few years, it's not going to happen anyway, not in a few years. Use those years to actually help the terrestrial renewable energy community find its legs. Everybody will love us for that, and then bring in space solar power, at which point we're not hurting anybody, because there's plenty to go around. So that's, and we think that can work with the usual, as John Mankin says, anything can be shown by computer graphics. And suitably adjusted economic modeling. But I think with reasonable parameters, we can show. And Carlos Rios is our digital media expert, who could not be here either because he was up late last night uploading a gigabyte video onto some server. And we are from the Georgia Institute of Technology, the School of Aerospace Engineering. So here's a, I forgot, yeah. Here's a summary of the paper. Yes, there is a huge need for electric power worldwide. And our perspective in the US and Western nations, or even Japan, may be a bit distorted, because we tend to think in terms of competing with the extremely efficient grids that we have and our extremely efficient utilities. And that is not the reality in most of the world. In most of the world, the power cost that people might afford to pay may be low, but only because it is heavily subsidized by the government, which is really not a sustainable situation to expand. So we should not just limit our thinking to competing with the $10 per kilowatt hour, et cetera, et cetera. And the people who don't have any money actually pay exorbitant costs for the first few watts or watt hours that they use. Even if I take the argument, I don't have to take the argument that Having the power to make a 911 call is a life and death situation which cannot be measured in money. I don't really have to make that argument because the reality is that if you look at the cost that people actually pay for the alternatives to having a nice power grid, they are truly exorbitant. So again, we should think a little bit beyond these things. What space solar power in general does allow, and the concept that we are presenting does allow, is delivering power even on a retail basis to people who don't have any other means of getting to that. Now, we have this crazy scheme that I call the space power grid. And the basic difference in the thinking there is, I say, let us not try to fight with the terrestrial energy community. We are not big enough. We cannot beat them up. They will beat us up. Or they'll just ignore us, which is what has been happening. However, they have serious problems, as you just saw. And the renewable power community has very serious problems. They cannot compete with the nuclear or cannot even compete with other things. Europe is facing extreme problems with the move to go to wind energy and all these things. So they have serious problems, and maybe we can help them. So that's what we say. Forget about generating power in space for